Yeah.
We were part of it.
All right, everybody. Thanks for coming out tonight. We've got a great attendance. This is I think this is actually this is more than we usually get by quite a bit. So nice. We have a lot of really great talks upcoming and a lot of really interesting events coming up soon. The next thing that we want to announce is on April 3rd, we're going to have a Boston area optics professional networking night. This is a new thing for us. We're going to be having an aeronaut brewing. It'll be sort of a come out and try to recruit people, have a beer, meet folks who you don't are outside of your usual circle. We're trying to have that closer into the city to try to get more of a student crowd and sort of harness the emerging talent pipeline. So we're really excited about that. All of these events, I should note, are on our website, NES-Optica.org. So please sign up on that. We'd love to see you there. Other things that we have upcoming, we've got a bunch of outreach events in April. It seems like all of the schools want to do their outreach event all in the same month. So we've got things like Lincoln Science Night in Brookline, which is going to be 4 to 8 p.m. on April 11th. That's really fun. 200 students get them like thrust upon you, and you just got to hand out diffraction glasses and teach them about rainbows for like 4 hours. It's awesome. Science on State Street out in Framingham, April 26th. That's a Saturday. That's noon to 3 p.m. That one's a lot of fun too. That's an outdoor event. We're going to have diffraction glasses because that's the best thing ever. I think that's a more adult crowd and more college students. Should be a lot of fun. We've got 2 talks coming up also that I wanted to announce. April 10th, not that long from now, is going to be our next a monthly talk that's uncovering the pathways of excitation energy flow and light harvesting systems with ultra broadband 2D. Sounds awesome. And then the big highlight of the year, May 8th. Suzanne, who goes first?
Yeah, but I flipped on it.
Uh-oh.
I did. I changed the talk this afternoon. So it's not what you got online. So sorry. I was going to talk about innovation and IP, but what I decided to do was talk about lessons learned working with the military and law enforcement.
Sounds awesome. And that one's at Opticos. The food is really good. The crowd is really good. The vibes are really good. And the speaker is going to be fantastic.
And the alcohol is really good too.
What's that?
And the alcohol is good too.
Oh, yeah. That one has an open bar.
No wonder that's so good.
So, all right. So with all those announcements out of the way, I want to introduce our speaker tonight, Dr. Amos Meeks, who's going to be talking about some of the really cool things he's doing with Irradiant technologies. So without further ado.
Great, thank you. Hi, everyone. Thanks for coming. So my name is Amos. I'm the CTO here at Irradiant Technologies. And at Irradiant, we really believe that 3D nanofabrication unlocks the full potential of optics and photonics. Right? If you think about how optics are made, you have sort of free space optics, which has been around for quite a while. Gives you kind of full 3D control over light. You can take many different sort of optical components and arrange them in 3D space. But you end up with systems that are sort of very low throughput to build these systems. They're bulky, they're expensive, and sort of slow to turn around. People are trying to solve a lot of these problems using sort of integrated optics and photonics, taking technology that was developed originally to do sort of nanofabrication for electronics and then apply it to optics. And this has a lot of advantages. It's a very mature technology. It can give you very sort of high throughput of very compact and affordable devices. But because of the difference in physics between electrons and photons, you're essentially fundamentally limited to sort of a single 2D plane or sort of separate 2D planes for optics, right? And this is if you have electrons in a wire and you want to go from a plane up into Z with like a through silicon via, something like that, you have a sharp right angle bend, electrons follow that, no problem. But if you have photons in a waveguide and you want to go up into Z, something like that, you have a sharp right angle bend, you're going to lose pretty much all of your light. Right? So photons really want gradual changes, typically both in geometry and in materials. And here's another issue here where typically it's binary patterning of material. You either have a material or you don't have a material. And so if you want to get sort of smooth gradients of phase or index, you have to play a lot of difficult tricks. And then economically, it really only works for very large volumes and has a slow turnaround time, of typically months. If you think about what an ideal platform for making optics looks like, it's something that sort of combines the best of both of these, where you can do kind of full 3D control over gradients of materials with nanoscale precision to make compact and affordable devices that can be sort of where you can do both rapid prototyping through high throughput production in the same platform, doing large and small volumes with a very fast turnaround time. And so this is what we're doing here at Irradiant, making what we call the world's first 3D nano optics and photonics foundry. We can fabricate any possible 3D geometry. It doesn't need to be self-supporting or contiguous. We can do it with deeply sub-wavelength resolution, down to tens of nanometers if necessary. But in a lot of cases, we found actually a few hundred nanometers is a lot easier and perfectly sufficient because we can directly pattern gradients of refractive index. And we can do this with an index contrast from less than 0.1 up to above 0.5. So an index contrast comparable to the contrast between glass and air. And then we do this with a set of materials that are compatible with PICs and fibers. This is primarily polymer and nanoporous silica, but I'll talk about other options that are there as well. And then there's the potential to do multi-material patterning with this platform as well, where you can directly then combine dielectric materials for optics with conductors or semiconducting materials. And then economically, we use an ultra-fast digitally controlled 3D lithography process that we developed. That means we can go from rapid prototyping up to mass manufacturing of up to millions of parts per year per system, still using the same technology and platform. And then with this, we've been able to demonstrate and create a wide variety of different sort of optical structures, lenses, filters, waveguides, and reflectors for routing light around. I'll talk a bit more about all of those. But in general, this sort of builds into our vision for creating essentially sort of lithographically defined and monolithic free space optical microsystems. So we think really trying to do for optics what planar nanofabrication did for electronics, where before microfabrication, you had separate resistors, capacitors, transistors. You had to solder these big bulky components together, and then planar fabrication processes came along. Now you can take those, directly miniaturize them down, and integrate them into a single platform. So we can do this now with optics, where you can take your full sort of optical setup like you might have on an optical table and directly miniaturize that down and embed that 3D into a single monolithic structure. And then, so in terms of what these capabilities, these for sub-wavelength 3D fabrication of optics enables, you can do these sorts of free space and integrated optical components. So I mentioned lenses here. These can be, plano-convex, biconvex, essentially doublets, because we have this refractive index control. Gratings, we can do prisms and beam splitters for routing light around. And then you can also make sort of more traditional sort of waveguides and ring resonators, but in 3D. But then going beyond this, you can start thinking about sort of inversely designed and multifunctional components with novel capabilities. So for example, so-called deep diffractive neural networks, which are essentially a series of phase plates that are precisely made with wavelength resolution and precisely aligned, and essentially take an input optical image. You can think of that like a complex valued matrix where you have a phase and an amplitude at every point in space. And then at each phase plane, that's sort of like an element-wise operation on that matrix. And then you get free space propagation, which is roughly equivalent to a Fourier transform. And then by cascading many of these together, you can essentially do arbitrary linear matrix operations on this input image. So these have been used for things ranging from basic image identification to multispectral imaging, phase imaging, and a bunch of other things. And then you can think about making sort of volumetric optics, and even if people have heard of meta-optics, volumetric meta-optics, where you can combine many different capabilities into a single compact structure. So this is an example of a structure that sort of takes broadband unpolarized light in, and then with a wavelength scale structure, splits it out by both color and polarization at the pixel scale. And then we can sort of take optics and make them flat and create these sort of multi-layer, what we call sort of multi-layer meta lenses, which potentially solves a lot of the issues that meta optics and meta lenses have had. And then you can take all of these and put them together. You can take all of these components and build them into this sort of three-dimensional microsystem, potentially also combined with sort of underlying structures, PICs, fibers, and create lithographically aligned monolithic 3D optical microsystems. Okay, so how does this work? Sort of the core process here and the core innovation on the material side is to pattern material inside of a nanoporous scaffold. And when I talk about nanoporous scaffold, this is kind of what that looks like. This is a nanoporous silica material where, kind of at the macro scale, it looks like a very, transparent kind of dull piece of glass. But then if you zoom into the nanoscale, you have this highly porous nanostructure that's very sponge-like. And so this is typically about 80 to 90% air. You can then take this sponge-like structure and fill it with a liquid patterning solution, such as a polymer resin. It can be other things as well. And then we do two-photon lithography to essentially attach this patterning material or use it to fill in the pores of this scaffold. And then we can wash out anything that hasn't been patterned. So you're just left with these three-dimensional structures embedded inside of this porous scaffold material. And so it's the scaffold that gives us arbitrary 3D geometries, right? Because we're not trying to build up off of a 2D surface. We're actually filling in pores in a 3D structure. So so it's everywhere supported by the scaffold, and you can make arbitrary 3D geometries. And then this is what it gives us our gradient index properties. Because, for example, if this is a polymer resin, just by controlling the laser power, you can control the degree of polymerization, and you can control the degree to which these pores are filled. And so then you end up with a sort of nanoscale mixture of polymer, air, and silica, where on one end you have sort of the empty scaffold here. It's about 80, 90% air, so has an effective index very close to 1. On the other end, you can fully fill it in with polymer. This gives you an effective index close to 1.6. And then by controlling the degree of filling in, you can get essentially any index in between those extremes. And then at the end of the day, you're left with a full kind of assembly or optical microsystem that is embedded in a monolithic structure that's mechanically robust for packaging and integration. So I talked mostly about silica and polymer, but we're actually building up a library of different options for scaffold and fill materials. So in addition to porous silica, we can also do this process inside of a polymer hydrogel, which you can think of as kind of like a nanoporous polymer structure or scaffold, which you can then actually dehydrate down and shrink down by a factor of 10 or more. And that's what gets you tens of nanometer resolution, if that's necessary. In a lot of cases, we haven't found that's necessary. On the other hand, you can directly essentially porosify a silicon wafer and then fill in materials in the silicon wafer. So this can also be sort of compatible with traditional kind of wafer scale processes. And then in terms of fill materials, I mentioned resins, which give you polymers, but we also have a process where we can essentially pattern functionalized dye molecules that have a specific chemical group that we can then attach a variety of materials to. So while resin just gives you polymer, with this dye, you can essentially, we've shown that we can grow metals. So we've actually made conductive wires with a conductivity comparable to copper. And you can do sort of other inorganic materials such as metal chalcogenides like zinc sulfide or lead sulfide, which lets you then get higher index contrast or expand out into other wave bands like the mid-wave or long-wave IR. And I want to say at this point, if people have kind of questions or things, feel free to jump in the middle. I'm happy to do that. Yeah.
Maybe you're getting to some examples, but have you played with biological hydrogels? It's like blood clot type of fibrin.
Let's talk about that afterwards. I think that's less of the focus, but there are things we can think about doing there.
What wavelength are you trying to work at?
So this really is a function of these materials. So this sort of porous silica with polymer is kind of the most mature of our material platforms. A lot of this work was sort of pioneered by our collaborators at UIUC. This works pretty well for kind of the visible through shortwave IR. So these scaffolds, you do get Rayleigh scattering. I'll talk about that in the next slide. So that starts being fairly significant or noticeable down into the blue. And then silica and polymer are quite absorbing in the UV. And then they're nice and transparent up to the shortwave IR, but once you get into the midwave IR, the polymer starts being pretty absorbing there as well. So that's where we're looking at some of these alternative fill materials like zinc sulfide, which can be nice and transparent up to higher wave bands.
Yeah. For this type of application, for two-photon.
Yeah. the depth limit, I can talk about that when I talk a bit more about the lithography step, but essentially it's the working distance of the objective we use, which we have some pretty nice objectives that have up to like 8 mm working distance. So we haven't found any applications that actually need that amount of depth so far.
So maybe similar to that. I mean, so you raster scan, is that what you do?
I'll talk about that later. Yeah, we'll get there. Cool. So talking a bit more specifically about these highly transparent nanoporous scaffolds, we've sort of developed and we make these in-house. This is an example of something we make currently. This essentially disc that's about 3 centimeters in diameter. We can control the thickness. Sort of standard for us is about 1 mm thick, but we can go down to, you know, a few hundred microns and up to basically, you know, close to a centimeter, where you start running into issues with the working distance of the objective. These have a porosity, or we measure the direct refractive index directly. It's can range depending on how we make these, from about 1.01 to 1.05, and that corresponds to porosities of about 88 to 98%. And then we can measure loss by basically, you know, taking a picture, sticking, having a reference, sticking the scaffold in there and looking at the difference between them. And we get sort of average loss in the visible of roughly, you know, 0.067 dB per millimeter. This is at visible wavelengths. It's primarily from Rayleigh scattering. So as you go out to longer wavelengths, this decreases, of course, with the wavelength to the pattern to the power of 4. So it becomes even much, much lower as you go into the near and shortwave IR. And then currently we're making these out to these sort of 30 mm diameter cylinders. But that's mostly a function of the equipment we have. So we have a new piece of equipment coming in that we hope will get us to about 100 mm by the end of this year, and then potentially can scale up from there. And then you can also directly cut these to pretty much any desired shape, either through laser cutting, or we found you can actually directly machine or mill them as well. And so this sort of polymer in porous silica scaffold, this is sort of the most mature process. This gives us an index the maximum index contrast comparable to that between glass and air. And so we measure this by making these sorts of triangular prism structures called Fresnel biprisms, which you can then send a collimated laser through. You get this then tilts these two beams by an angle that's defined purely by the refractive index difference. And then you get an interference pattern where the fringe spacing of this interference pattern tells you what that index contrast is. And so from this, we've measured continuous control essentially of this effective refractive index from less than about 0.1 up to a little above 0.5. And in absolute terms, from about 1.05 to about 1.55. And so this amount of index contrast is enough to enable efficient, basically 90-degree total internal reflection. So we've actually made these TIR prisms pairs where we have light that sort of shines through the substrate. You shine it onto one of the prisms, it bounces between and comes out the other side versus going back through the substrate. Yes.
So the sensitivity is actually very high. How do you stop the polymerization? You've got the two-photon polymerization. Is there any issue with aging and exposure to? Not that we've seen. So we have samples like these with these prisms that we've left and aged for a few months now, and we take them out every now and then and measure them, and we haven't seen any difference. But if you're using them actively, and probably at a different wavelength, obviously, but if you're using them actively, do you have? So that's another reason that like UV, for example, is not compatible. You get a lot of scattering, and UV definitely will age and yellow and cause crazing and things like that. So we tend to try to avoid the UV for a lot of shortwave IR 1550, 1310, that sort of thing. Not really much interaction there. Okay. You do, I can talk about this briefly in the next slide, but you do get it at high intensities. We do start seeing some degradation, but it's quite high power densities. Okay.
What kind of power? Watt?
I will talk about that in a couple seconds. Okay, actually it's like 2 slides, but I will address the power directly. So in terms of things that we've made, we're just going to sort of go through a library of things. So we've demonstrated a wide variety of sort of geometric, diffractive, and grin lenses with any kind of profile. So these range from sort of standard geometric kind of micro lenses. One interesting thing we can do is directly put gradient index anti-reflection coatings on these, right? This is just a matter of going from the high index of the lens itself to the low index of the background over sort of a micron scale distance. And the nice thing about this is it both, gives you AR properties, so you get higher throughput, and it smooths out a lot of sort of like printing defects. So we can actually print at relatively more coarse resolution than maybe with like nanoscribe or more traditional two-photon polymerization, and still get a very, very optically smooth structure. We've made hybrid lenses where you can essentially combine refractive and diffractive structures, taking advantage of the opposite signs of their dispersion for chromatic aberration correction. But then, we can also just make fully grid lenses where geometrically, this is just a flat puck of material that has a higher index on the outside and a lower index, higher index on the inside and a lower index on the outside. And that can be essentially any profile. In this case, it's a linear profile. So this functions as a grid axicon. But then we can make fully 3D gradient index structures. So this is, I believe, the first published example of a visible wavelength spherical Luneburg lens, where a Luneburg lens is a specific spherically symmetric refractive index profile that has the interesting property of taking collimated light from any direction around the sphere and perfectly focusing it to the opposite side of the sphere without any chromatic or other aberration.
Oh, perfectly.
I mean, in theory, right, like fully perfectly. In practice, I don't know, there's always deviations and errors and that sort of thing. But like, I guess what this is showing here is this is 488 nanometer light, and this is 633 nanometer light, and they form basically fully diffraction limited spots on the opposite side of this sphere, just from this single element. And then, of course, we can take these and build them up into full sort of arrays. So this is sort of an array of micro lenses that we've measured with like 93% shell ratio, and we can make this sort of even centimeter scale arrays filling up these full scaffolds that I talked about before. Yeah.
Is one of the advantages of photons or 3D print this, right? Are you getting resolution for the printing like inherently aligned? Like, or do you have to do some extra alignment?
No, we get that for free. So I will talk about that. That is one of the big advantages of our platform for a lot of applications, I think, is we can essentially shift active alignment from, having different fibers and components and shift that into the lithography step where we need that for free, basically, to place things accurately.
Some complex systems where you might not have build up optics for testing.
Yeah, I'll talk about the active alignment in a couple slides. Okay, so in addition to sort of like lenses and free space components and that kind of thing, we can also do sort of essentially 3D waveguides and integrated components in any geometry. And so we've been able to demonstrate sort of fiber to 3D waveguide interconnects with less than 0.5 dB insertion loss. And I think there's even a lot of room for improvement there. The waveguides have been demonstrated with about 2 dB per centimeter propagation loss. Again, I think there's some room for improvement there. And then these optics are very polarization insensitive and broadband. And so this is showing a range from 1250 to 1650 nanometers, but this has actually been tested down to like 780 or something like that. And again, you get pretty consistent loss in that range until you start getting to the range where you're start getting a lot more loss from the Rayleigh scattering that I mentioned. And then you can build sort of high Q factor ring resonators. So this is an example of a ring resonator with greater than 73,000 Q factor. And here's where I'm going to talk about the power density, because basically the data we have on the maximum power density right now is from these sorts of structures and seeing how much sort of continuous wave power you can put into these. So these were tested with about 20 milliwatts continuous wave power. And then this Q factor corresponds roughly to about an 80x enhancement of power density. So that's about 1.6 watts that is then confined to these waveguides are about 1 micron in diameter. So about 1.6 watts in roughly 1 square micron. Then you start seeing slow degradation of function over the scale of hours. The Q factor sort of slowly degrades. We suspect this is primarily from sort of thermal degradation of the polymer. Right, but that means that, if you're spreading this out, like actually want to put this through a lens or something, 100 micron or so lens is now 10,000 cubic or square microns. So you can think about having sort of 10,000 watts through that before you start getting this slow thermal degradation. So depending on the application, it can go to quite high powers. Yeah.
What's the rule of thumb for the DNDT of these? Does it follow the material you're patterning into it, or the CTE of the microstructure?
Yeah, that's something that we're working on measuring now to get very accurate data on. So I don't have a good answer for you. What I can say is that we essentially have enough design freedom here to compensate for essentially as much DNDT as you want and other things. I think we've been doing some designs recently for sort of like a lens basically that goes between like 4K and room temperature and has no change in performance. With basically assuming polymer levels of DNDT, which is quite high. So then you can directly integrate these sorts of waveguides and things in 3D with miniaturized free space optics. So this is an example of sort of 25 micron scale McNeil polarizing beam splitter that is then directly integrated with essentially lenses and 3D waveguides to take unpolarized light and split it by polarization. And then, of course, we can make diffractive devices ranging from both these sort of simple 1D diffraction gratings to these more complex 3D diffractive structures like these deep diffractive neural networks that I talked about before. And then we can create, essentially sort of flat optics where people are familiar with meta lenses, meta optics. Those have are pretty interesting to be able to miniaturize things, but have a lot of issues with chromatic aberrations or things like that. And I think the way we think about this is essentially, just as with a full, optical stack with different kinds of lenses, you need many components in that stack to correct for all the different aberrations that you need. With meta optics, you also need essentially a stack of optics to correct for all of the possible aberrations. So when you're just making one or even two planar structures, it's like trying to make, a fully aberration corrected lens with just, or objective with just two lenses. But in our case, we can do essentially fully arbitrary 3D optics, so we can stack as many kind of lenses as we want up to correct for a lot of different aberrations. And this is an example of a 4-layer optical optic that we've made. It's about 300 microns in diameter, has a focal length of about 145 microns, so an NA of about 0.7, and this is about 2 microns thick, corresponding to these 4 layers there. And then we get this sort of lithographic alignment to underlying structures for free, which we think can sort of fundamentally eliminate the need for active alignment. So our lithography tools are also essentially microscopes. So this is an example image where you can see a fiber array in here, which we've then printed these sets of lenses and prisms on top of that. And these are aligned to the center of this fiber with less than, with sub-micron accuracy, because we need that level of accuracy anyways in order to build these optical systems. And so this sort of lens and prism pair means that you can now take this light, you can collimate it to whatever size you want, and then you can bend it and send it off to whatever direction you want. And so what this means is you can essentially build kind of collimated beam connectors where you have like a sender on this side and a receiver on this side, where now instead of needing to line up, to a 10 micron mode field on a fiber or, a 2 micron mode field on a PIC, you just need to align this sort of hundreds of micron expanded beam between the two, where then each one separately has this lens prism pair printed on it. And then this expanded beam gives you tens of micron alignment tolerances, which is enough that you can then essentially mechanically confine this and still get low loss. And so you essentially end up with pluggable expanded beam connectors because you've shifted all of that active alignment and the placement of these components into the lithography step where you need that.
Are you able to explain this?
Yeah. I think I have a slightly old slide here. So what's missing here is kind of like, imagine that there is a fiber end here, And then the scaffold is kind of around this structure here. And then you have these components printed in polymer inside of that scaffold. That's one thing. And then you have just kind of air. And then you have, you know, another fiber or pick over here and another sort of scaffold that's separating from it. And so the output of each of these is this sort of several hundred micron beam going in some direction, right? And so as long as you line these up properly, this expanded beam will then be received here. It'll be straightened out and then it'll be focused back down to couple into the pick or fiber on that end from the pick or fiber on this side.
It's because they're coupled together.
So it's because these components are perfectly aligned here, you get this very regular expanded beam. And now what you're, instead of trying to match, say, like a 10 micron mode, which is typically what you're trying to do if you're going like between fiber to fiber, you need to get 10 micron, you have a 10 micron mode, so you can only withstand like roughly 1 micron of misalignment between the two before you start seeing like 1 dB loss. Now the thing you're trying to align together is like a roughly 100 micron mode. So now you can handle roughly 10 micron misalignment for still the same loss that you would get for 1 micron in the 10 micron fiber case.
Once you started building that, sound like the secret sauce that kind of
a lot of people are very interested in this. We think we're very excited about this. Yeah. Yeah.
So I'm still grappling with, I mean, you obviously work this out because you have these great, you know, devices. But like, is there a high threshold, a sharp threshold of incident, you know, intensity and the chemical transformation? Like you talked about, maybe hydrogel was evaporation. I mean, if you have a lens, a microscope lens focusing the light down, it's gradually increasing in intensity. At some point, it's going to trigger more and more and more of that reaction. Doesn't that affect your resolution? And maybe it's a depth resolution.
Are you so there's the patterning step where we make, so are you saying like if we print a lens and then we're trying to print structures?
I'm just talking about printing. Yeah,
yeah.
Exactly.
So typically we print from kind of the furthest back up, right? So we're like, if we're starting here, we print this lens and then we print this so that, you know, we're never sending our light through this structure.
And then so, but why, when the light is going through the volume prior to its focus point, isn't it transforming the material? I mean, I understand when it's at broadest.
I'll be talking about that soon. It's a two-photon lithography process.
Right.
That's why. I'll talk about that then. Yeah.
Viewers and rings, layer by layer.
No, I'll talk about the lithography process. That's coming up soon. Yeah. Right now we're focusing on applications and materials, but we'll get there. And so this sort of builds into our vision for these sorts of integrated free space optical microsystems, where you can now have all the sort of components you might have in an optical table, where you're routing light around using lenses and prisms. You can have polarizing beam splitters, dichroic mirrors for splitting, mux demux. You can have expanded beam connectors to connect to fibers or picks. And then for active things that we can't pattern, like photodetectors, lasers, sources like that, we can, you know, stick our scaffolds on top of a pick and do the and then print a line to these structures and have those directly integrated. And then also for materials that maybe we can't make, such as like a magneto-optic material for an isolator, you can actually essentially cut pockets out of these scaffolds, stick them, you know, plop the material down into it, and then write the optics around that material in 3D. Yeah.
Can you give me an idea about the scale of that?
Yeah. Think about maybe like millimeter scale for the whole thing, and then like, you know, tens to hundreds of microns for individual components.
Couldn't you, while you're printing, magnetically pull material while you're printing to give you a magneto-optical structure?
I think that is likely possible. We haven't tried to do it yet. I think that'd be a great thing, like, you know, down the road, or for someone in academia to play around with that. I think it's pretty interesting.
You can also make a chiral material.
Yes. Although I think we can also make essentially anisotropic material here just by printing sub-wavelength anisotropic structures with that. March. And so this gives you sort of full 3D control and routing of light in 3D. And so you can make complex free space systems that are fully lithographically aligned. So all of the individual components aligned during the lithography step, giving you sort of one platform for heterogeneous integration between all of these different modes, fibers, picks, free space. So all of this is based on sort of two fundamental innovations. The first I've mostly talked about, this is the material side of things, doing two-photon lithography within a 3D nanoporous scaffold, where the scaffold gives you the arbitrary 3D geometries and the gradients and their mechanical integration. The second is that this really only matters if you can scale up two-photon lithography to sort of industrially relevant scales. So to do this, we've developed an ultra-fast two-photon lithography process we call line scan temporally focused two-photon lithography. And this gives you economical high throughput production where you can use the same system for, it's digitally controlled, so you can do rapid prototyping with fast turnaround times and also scale it up and then still get nanoscale resolution in any geometry. So we're going to talk a bit more about this and maybe answer some of the questions about the lithography step. So it's two-photon excitation that enables nanoscale printing. So if you think about, if you're all familiar with like SLA 3D printing, Formlabs, that sort of thing, you can think about that as sort of one photon polymerization, where you shine your light in. In this case, what you're seeing here is fluorescence from one photon absorption. So you get the highest intensity at this focal point, but you get a lot of that background interaction with material outside of that, right? So if this is polymer, you would start getting polymerization here and here, and that's a problem. In two-photon excitation, rather than each photon individually having enough energy to cause your reaction and initiate polymerization, each photon individually doesn't have enough energy, but at extremely high optical intensities, you have a very small chance of absorbing two photons essentially simultaneously. And then the energy of those two photons added together gives you enough energy to cause a reaction. So in this case, again, you're seeing fluorescence, but now the fluorescence is very tightly confined just to this focal point, and then it drops off very quickly away from that. So you're basically getting essentially absolutely zero interaction outside of that particular spot in 3D space.
Drop off this.
So it's going to depend on your focal spot size and a lens. Highest magnification typically is like 200 nanometers laterally. People have played some tricks, and if you move to lower wavelengths for this, you can get down to like 100 nanometer lateral distances.
And so all your processes were two photon. I remember you said something like the hydrogel was evaporated.
That was
the one.
it's still two photon for the patterning. The hydrogel, then you dehydrate it and that shrinks it down. So that's like a bulk step. It's not part of that. Yeah.
I think I understand that the two-photon transition is very enough linear and you can focus it tight when it drops off laterally pretty quickly when you don't have the process pretty much again.
Yeah, so it's the PSF you're going to get here is essentially equivalent to any standard PSF from a lens. So say if it's roughly 200 nanometers laterally, that's usually roughly like 500 to 600 nanometers axially. Yeah, so it is somewhat anisotropic. Between 2 and 3 to 1. And so the typical way of then making things is to take this point in space and then raster it around and try to build up your structure. This is called point scan, and it's just fundamentally too slow, right? So if you think about an example part you might want to make, this is a lens that's about 1 centimeter in diameter, 10 microns thick, so still a very, very sort of thin lens. Making this using a system like the Nanoscribe Quantum X, this has a volumetric print rate of about 0.05 cubic millimeters per hour at its highest resolution of about 200 nanometers laterally. And so this component is about 1 cubic millimeter, which means it would take about 20 hours. So you could make about one of these per day or about 400 per year. This is, fine for sort of academic R&D settings, which is typically where these are used, but not very practical for actual sort of industrial use. So the way to improve upon this is rather than patterning one point at a time, you want to pattern many points. And similar to sort of where one photon 3D printing, such as Formlabs, have gone from sort of taking a point and rastering it around to now DLP, where you're actually projecting a whole plane, you can do the same thing with two photon. And so this was demonstrated in this paper from 2019 that is not in any way related to us, where essentially they take their femtosecond pulse laser, which you need to get this two photon effect. They project it onto a digital micro mirror array, DMD, which has these mirrors that can basically be flipped on or off or on. And then you essentially image that acts as sort of a digital mask that you then image into your resist material, project that mask, and you can create structures. And they were able to print polymer in air. Yeah.
Maybe you were asked us to do any holographic fixed stripe for high throughput volume.
That is, I think that's an interesting thing. We're leaving that to the academics for now, but we have some interesting ideas around that, including like, we can make the holographic elements that can then be used to project things, and there's some crazy ideas there, but not stuff that we've done so far.
Yeah, I know that you can like split light up small.
Yep. Yes, you can potentially do sort of full 3D structures in a single shot with holographic patterning. It's very interesting.
Reasonable size lens to EOP, the pixel size, the individual beam size is way small. Is that true?
I'm not sure if I'm totally understanding your question, but like sort of the voxel size you get here, the resolution ends up being roughly equivalent.
Previous slide, you explained the focus.
Yeah.
Very tightly, but then you have high resolution, but when we focus tightly, the gaps can be, we need large gaps. So your individual lenses were much smaller. Does it mean your resolution is inversely larger?
So I think I'll sort of get to the answer to this
You're
question.
gonna be able to talk by 8 o'clock.
Yep.
Okay.
Yeah, this is basically the last section of things. Yep. So this is sort of the fundamental problem with this approach in this paper that they kind of buried in the SI, which is that when you're making sort of diffraction limited line structures like this, you get nice diffraction limited resolution. And there's an extra piece here that I didn't mention because it gets a little bit technical, but this DMD also acts as a diffraction grating, and you get an effect called temporal focusing, which can essentially compensate for 1 degree of spatial defocusing. So when you have a diffraction limited line, you basically have 1 dimension of spatial focusing, 1 dimension of temporal focusing. You can recover that full sort of single point diffraction limited resolution. But as soon as they start going to thicker lines, you start very quickly losing your axial resolution and get very extended PSFs, which then means you're losing the submicron resolution you want from 2-photon, and it means now you have a resolution that changes as a function of the shape that you're trying to make, which is pretty difficult to deal with in practice. So we've solved this problem, and the way to solve this problem is that we stick essentially a cylindrical lens in front of the DMD. So rather than illuminating the full DMD, we focus the light to a line on the DMD, and then we mechanically scan it across it. So that from the photon's point of view, at any instant in time, you are patterning a diffraction limited line and you get that diffraction limited resolution. But then as long as you can scan it across the DMD faster than the DMD can actually refresh based on the hardware, you can still essentially go at the full speed of patterning entire planes at a time. Yep. So these DMDs have a binary refresh rate of around 15 kilohertz, which is easily mechanically scanned with a polygonal scanning mirror. And so we've built these and have demonstrated very large volumes that maintain good resolution. And so if you sort of compare the throughput to these, this really enables the scale that can make things practical. So I talked about nanoscribe before. These sorts of point scan systems have a maximum throughput at their highest resolution of about 0.03 cubic millimeters per hour. We do use point scan sort of prototyping systems. You can use faster scanning like res scanners. These can go about 100 times faster. So you can get, 2 to 3 cubic millimeters per hour. And then this 2019 two-photon DLP paper, they demonstrated a throughput of about 33. Sorry, I guess I should be going through these. So they demonstrated a throughput of about 33 cubic millimeters per hour. About 1,000 times faster than this, but of course with the big asterisk here, if that's only for sort of sparse diffraction limited lines. And then we've sort of demonstrated a production system that goes up to close to 200 cubic millimeters per hour. So now sort of 10,000 times faster than these point scan systems. So whereas a point scan system, you could make maybe 400 of these components per year, 10,000 times faster, you now start talking about 4 million components per year per system. And then this is actually still very far from kind of the full theoretical DMD limited throughput of these sorts of things. So we think there's several orders of magnitude improvement here. And we actually have a pretty large 2-year DARPA program right now, where one of the main focuses is on taking this speed that we've demonstrated already and increasing that by another factor of 3. So that's about the technical content. A little bit about us as a company. So the founders are myself and my co-founder, Dan Aran. We have a number of academic advisors from both MIT on sort of this sort of implosion fabrication with the hydrogels, as well as the temporally focused line scan lithography, and then folks at UIUC who pioneered a lot of this sort of polymer and scaffold processes. The company sort of started essentially in 2021. To date, we've gotten about 22 million in a combination of VC and grant funding. At the moment, that's primarily more than half grant funding. We're at about 23 employees, and we have about 21,000 square foot space in Waltham, Massachusetts. And so with that, I want to invite you to, you can see it for yourself. I have a few physical examples if people want to come up and see those after the talk. You can try it for yourself. So we actually sell these nanoporous silica scaffolds, and they're quite compatible with common commercial two-photon polymerization, such as nanoscribe or upnano, and common resins for that. And we can provide sort of protocols and advice for that. And then we're always looking to collaborate. We can work with interested people on sort of novel designs. I think there's a huge design space of what you can do here. We can do sort of prototype fabrication going up to sort of small scale manufacturing, and then hopefully scaling up to large scale manufacturing. And then we're always happy to collaborate on grants and kind of R&D. And so if people want to get in touch, that's my contact info. I also have cards that you can get to. But with that, happy to sort of conclude, I think, with plenty of time and answer more questions. Yeah.
You were saying that you scale the mix of refraction with intensity, is that right?
Basically, we can by controlling the laser power during that lithography step, you control the end effective refractive index you get.
You equate it all with like tuning the laser?
What do you mean by tuning the laser?
Sweeping it?
We use a single wavelength currently. I haven't played with that. I don't see much need.
Yeah, I'm just, it's curious, like what you could potentially do with that, 'cause there's like swept sources now. And then people use those a lot, like an alternative in like interferometric systems for polygon layers. Those polygon layers are kind of like noisy and awful in a lot of ways. And you can like use something around dispersers.
Interesting. Yeah.
So, how do you envision mounting your components in a free space environment?
Yeah. There are a lot of different ways you can think about doing that, depending on the needs. I'd say the most simple kind of brute force solution is you can just directly like epoxy or glue these onto structures or things like that. You can, I sort of mentioned quickly, you can basically machine them or laser cut them. So you can cut them to certain shapes and sort of fit them in or slot them into things. You can actually, we've been able to essentially use the polymerization process in lithography to tack them down onto a surface. You can functionalize like a glass surface and then polymerize and attach down onto that during that step.
Can you recommend a material that would match the CTE of your components?
Yeah, the CTE for them is pretty similar to silicon. It tends to be a little bit, I always forget if that's higher or lower than silica, but it's closer, usually closer to silicon than silica, but somewhere in between typically.
Yeah, I was curious, you mentioned offhand when Josh asked about the DMDT, about optics operating from basically with helium up to room temperature, I mean, 4K to 300 or something.
Yeah.
Were there any special design steps for athermalization, you know, the kind that lens designers have to do with macro optics or?
Yeah, I mean, we basically designed doing an optimization for that athermalization. I think the key thing is just we have so much freedom here that it becomes relatively easy and then is actually manufacturable, right? Because we can also manufacture basically.
And can the materials withstand repeated cycling? And the real problem with the ultra cold stuff is that.
Yeah, I think so. That is something that we have not done rigorous testing on, but like we have taken these, you can like dunk them into liquid nitrogen, take them out, you know, they work just fine. But I don't have much more rigorous testing than that at this point.
I know a lot of IR optics that I've played with has trouble even going, repeated cycles between just, liquid nitrogen 77K and
Yeah.
temperature for a few hundred
Yeah,
cycles.
so that's one of the, I think that is, once you do that testing, I expect it will be good, because that's one of the nice things about having everything fully integrated in this structure is there's just, it has some flexibility to sort of expand and contract without falling apart, but then everything is being very tightly held, with nanometer precision to where it is.
Amazing.
As far as the standpoint, I think I understand the lateral patterning using DFT and the line approximately in C. How do you pattern multiple depths?
The most basic way to do it is just to step up through layers, right? Like we pattern this layer
Yeah.
and sorry,
Just
mechanically, yes.
Okay.
Yeah.
And then, so the associated question in depth, so the patterning in Z, is it like one layer pattern and then cures the polymer and then you rinse the rest and then do it again?
No,
Or you do it.
you don't need to rinse, right? So we have liquid resin and you go through and polymerize the full structure and then you wash out after doing everything.
So it washes out even from the area.
Yep. Yeah. I mean, if it's buried, if you fully polymerize it, there's not much to wash out. So, there are things, right? You have to be careful if you're making like a full shell where you want like a sphere that's very strongly polymerized so it forms a boundary and then not have it polymerized on the inside. That can get tricky. We haven't found applications that need structures like that. If you do, there are ways to try to deal with that depending on the constraints of the application.
I think you did say it, but could you remind me what the loss is of these?
Yeah, so most of the loss comes from the background, the Rayleigh scattering of these structures at like visible wavelengths. The number I had was about 0.067 dB per millimeter. So 0.67 dB per centimeter. If you go into the IR, that drops off pretty quickly. And then, there's separate loss for like loss of a component like a lens or a waveguide or things like that will have their own. Yeah.
Can you print directly on the substrate? And in particular, can you print on the face of the fiber?
Yep, absolutely. So typically what we do is actually like stick our scaffold down onto the face of a fiber and then print into it. But we can also do things like, you could have an air gap between the scaffold and a fiber or a pick. You can print in air here and then go into the 3D structure in the scaffold. You could print something we've toyed around with is like basically printing like a receiver or like in polymer outside of it. And then you can stick a fiber into that. So, yeah.
One last question. You said that most of your losses are due to Rayleigh, but you're not seeing any diffraction from your spots when it goes into open air?
Like just through the scaffold or like from a printed lens or
from a printed lens or structure that you printed new?
Not significantly. If you look at, so for example, these are lenses that we print because we can do that sort of essentially anti-reflection gradient index sort of smoothing, you get very smooth structures. You can smooth away some of like, the lines that you might get if you're raster scanning or things like that.
Yeah, we have a nanoscribe and we do see a lot of diffraction.
Yeah, that's basically because we get this gradient index control, we can smooth over all of that. It makes a lot of things a lot easier than printing in air.
Mechanically, are these robust or they need to be packaged?
They're handleable if you're gentle. They're fairly brittle. If you put too much force on it, it'll break. If you drop it, it'll crack. Right. Typically you want to do some handling, but then like, I don't know, I have some of the examples here that are stuck down and like you can, if you have a structure on it, you can handle it pretty casually. Yeah.
So I don't know anything about aerogels, but the porosities that you quoted are very high, 88 to 98% in the silica aerogels. And you get a full, your polymer, which by the way, is it proprietary, the polymer?
We use off-the-shelf resins mostly.
Okay. How long does it, I realize these are thin, but how long does it take for that polymer to migrate in and not trap air pockets and stuff like that? What do you do?
So the getting it into it is actually quite quick. For that, you can just pull a vacuum and it will just like suck right into it. Getting it out is a little bit slower. You have to basically wash it in solvent. Typically, we do that with like it takes about a day or so to wash out. That's actually the main thing that limits the kind of like full round trip
Yeah.
time. But that's still, you know, a turnaround time of a couple days for custom optics, I think is pretty good.
Okay, thanks.
The hydrogel structure, hydroscopically, how do you control the water not leaching into the aerogel?
Yeah. Are you asking about hydrogels or the silica scaffolds?
The silica, either one.
Either one.
Either one will be hydroscopic.
Yeah. So we don't do much with hydrogels these days. It's a capability in our library, but we haven't actually found that many application people who care about having that level of resolution. But mainly you'd want to seal that up some way, right?
And then the other question I have is functionality. Can you create a functionality, say for instance, for a biological sensor?
Yep.
So you
Yeah.
increase or decrease the surface energy in a certain pathway.
Yep. So that actually, for the silica scaffolds, we can actually functionalize them or coat them in ways that make them extremely hydrophobic. So we've actually been able to make these where you can just dunk it. So normally, if you take one fresh out, you put a drop of water on it, it cracks and explodes. But we've made ones that you can essentially dunk and leave in water for multiple days at least, and they're perfectly fine because they just are so hydrophobic they exclude water entirely. But that can be biological structures too. And then I didn't put in the slides, but with that sort of chromophore to attaching different things, you can use that to attach biomolecules. So you can attach DNA, RNA, aptamers, proteins, fluorophores, you name it. So you can even pattern down to nanoscale resolution, you know, chemical or biological functionality.
Have you done anything with exosons?
No.
So, what's bad about this?
It's a relatively new technology, right? So like a lot of the questions we get right now are like, you know, reliability testing, longevity, things like that. We don't have good data on that. We're starting to get it, but like that takes time. You know, we're still working on scaling up our processes, right? So we can do sort of small scale prototyping, you know, maybe tens to hundreds of things, but we're working on building this up to manufacturing, hopefully over the next year or two. And then, you know, it still has polymer. So in situations where polymers are not great, so in space, for example, you know, they'll be degraded by cosmic radiation and things like that. And, you know, it's in a remote environment, you really can't have any degradation.
I guess like, you have to like.
No, but we don't need to, right? Because anything you'd want to do with a coating, pretty much you can do by controlling sub-wavelength refractive index, right? So I mentioned already basically gradient index AR coatings, the beam splitter that I showed.
If you have a substrate, can you spin it, for example,
Ah,
or deposit it?
okay, is that what you're asking? Not optical coatings, but like coating the scaffold material onto something.
Maybe a little.
Okay, I'll answer both. Right, so optically, right, like, you know, we can make, you know, essentially Bragg stacks for doing polarization splitting or color splitting or things like that.
Something like ultra like low light situations where you're really sensitive to losses.
I'm off on.
Right, so that's the gradient index anti-reflection coatings. We can do that everywhere, right? If you're interfacing this with a fiber, for example, right, you can put a gradient index at that interface in the structure, you know, do free space inside of our thing, gradient index at every single component of any arbitrary shape, so that you can potentially get very low loss.
I guess it's gonna be really hard to have active.
Yeah, so for now, we don't do active components. I think there is interesting possibilities there just because we have so much flexibility with our materials. It's on our like 50-year roadmap.
Like fiber optically just.
Right, or directly on top of a PIC or something like that that has modulation. We even think about if you want to have modulation, you don't need to have like a waveguide and ring resonators. You can just have like a square that you're actually bouncing the light in and out of, or sort of coupling into and then having a grating to couple back out of. So you can just do the modulation on like a 2D platform, like a PIC, and save all of the space that you would normally need to use for routing or shaping.
What's really cool is like a lot of the stuff you crazy expensive robotic system. free space.
To answer the question about like coating the scaffold, so no, currently, at least with the silica process, you can't really coat that because there is shrinkage in the process of making that. So typically we make them freestanding and then attach them down onto things. There is, with the process of peroxifying silicon, if you have a wafer or grow a layer of silicon, you can then peroxify that and could use that as a substrate. Is there a question back there?
Yeah, I was just curious, how many designs do you need to go through to meet your spec? So, for example, you accept a beam, you have a beam splitter, you focus to a particular, you focus both beams to, with two different lenses. How many designs do you need to do to meet that spec?
Right now, too many. Right, that's what I mean by like this being a relatively immature technology, is we're still trying to figure out a lot of those things and try to like basically build up a PDK. So we're trying to build up a library of like components that we know how to make. Once you have that, right, we've made 1,000 of this kind of lens or 1,000 of, it's just a matter of like change a little bit to get whatever focal length you want, but we have that parameterized, exactly that, then you can do many fewer iterations. And then the turnaround time is a lot faster. But right now it definitely takes quite a few to really nail something down. Simulation is hard because there doesn't really exist simulation software capable of doing these things, right? Because no one else can do this, so why would they make the software, right? Doing full 3D gradient index, simulations, that's not something you can really do in ZMax.
No, but there's
They still often don't. We have not been able to find a simulation software that allows you to do all of the things that we're capable of making.
like synopsis.
Even then, those are typically much more focused on like pick layout or things like that.
Yeah, so you're
right.
not using this.
No, I mean that's like pick layout is so far, right? That's completely 2D and binary material. It doesn't give you, it's not going to give you gradients of material. It's not going to give you full 3D sort of things. Yeah.
On the same vein, the inverse design process
Mhm.
used to get the shape. But if I want to replace one of the groups in my lens design with one of your elements, do I just send you a ZMax file and say replace that one? Or do you like, how do you do it?
Yeah, that is another sort of part of the pipeline that we're trying to figure out. Right now, we're trying to work with the design software we have. So we do a fair amount in ZMax and then port it to our own things to then figure out like the AR coatings and things like that and then print it. Yeah, what we're doing right now is not too far off from what's traditional, mostly because we're a little bit limited by the software that's available.
I don't have to be the one to decide.
No.
You do.
Yes, yeah. So we have a pretty good team of optical engineers and designers who are very familiar with our capabilities, and so we have to have ways of doing that.
I need to typically work with other entities that are looking to do development. It's like a heavy NRE.
There's a significant NRE part that's typically right. So what we found mostly is companies, they want a demo of something on a small scale, right, to something custom for them to show that it works and it's possible. And then we try to scale that into like, okay, longer term, like joint product development. Let's iterate and do all the reliability testing and things to make something that's going to be a finished product that then we can go to volume manufacturing with.
It's like a not your process.
Depends on what you want to do and how much money is involved.
All right, folks, it is currently 8:05. At 8:15, a janitor will come in and be very sad that we are still here. There's a very nice lobby out there with chairs.
Thank you. Great talk. Thank you.
Yeah, it's very nice.
Thank you.
If I want to talk to you about getting samples, do I email you?
Yes.
Cool. They'll be in touch. Yeah. Oh, one other question is, what kind of reproducibility, like that array that you're showing?
Yep.
What precision do you have, like variance of position across that array? Like variance in pitch, I guess.
Okay. Basically, that depends on the bidirectional repeatability of the nano positioning. Say, the one we use right now is not the best. It's about 200 nanometer We're moving to more 50 nanometer ones. You know, most of these things really care about like stimulated micron scale variation. So we haven't had any.
Great, thank you.
Yeah, thank you.
So on the slides, like on one of the slides, it had like the, like, I think it was supposed to be like, right, like, and then showed like the corruption. So does that work in reverse?
Excuse me?
In theory, yes. That's what it is. It's a passive component, so we have time.
So you could take the fiber optic, you could have that there. You have to code it, but just one more. That's you can have 60. And you can bring it later. This is really valuable for not to actually use the height. So you start to yeah. And then you're right. So there's
Yeah, I agree with you.
I don't know much.